let me talk about the Waveserver and store in Wave in a Box. So, yes, a quick outline. I'll talk about the Wave bus, whereby the Waveserver component. When I say Waveserver here, it's sort of a narrow sense of a certain component in the system, and the Wave bus, which is the interface by which it talks to the rest of the system. Then I'll talk about the data structures in there, the wave map, the wave container. I'll explain how the mechanics of applying a delta with operational transformation, etc. Then I will explain the commit notices and how that sets the requirements for the wave store implementation, for a persistent wave store implementation. I won't have a lot to say about the index, but and then I'll explain how the federation side of the Waveserver works, and end up by pointing to where the source code is, and explain sort of the current status of what's working and what isn't, and some of the things that are the next things we should be doing to it. So this is Alex's diagram from yesterday. I think he called it the server core, that the big box above the data store and behind the wave bus. So this is what is meant by the Waveserver in this talk, and it's indeed called the Waveserver in the source code. The wave bus is what connects it to the client front end and the robot gateway, and these clients of the wave bus, they are the ones that consume the deltas that are going through the system, and that and they're the ones who update the waves and submit delta into the Waveserver. So the wave bus, I think in the source code, it's called both. It's split across two interfaces. One called Wave Bus, another called Wave Provider. But I think it's useful to think of them as one. This is the interface between the Waveserver component and the rest of the system. It allows the clients to subscribe to all the traffic in the system that the Waveserver broadcasts to the clients. And the traffic is the deltas that are applied and commit notices, which I'll return to. But it means commit notice means that you get a guarantee that something has been persisted. And then the clients can call some methods on this interface. They can submit a delta. They can request a snapshot of a wavelet. They can look at the past deltas in the delta history of the wavelet, and they can, given a wave ID, they can ask for to look up the set of wavelets in a wave. As I look through the code in preparation for this talk, I realized that's not really implemented, but it should be. I should take a closer look at exactly how our client front end works. I think the thing is that we don't have user data wavelets and private replies and so on turned on in the Wave in a Box client yet. Therefore, we haven't this concept of discovering the wavelets in a wave have not been relevant yet. So the advantage of this particular diagram here and the division of labor that is represented here between the Waveserver and the client front end is that the Waveserver is not dealing with the session state of the clients that are connected to the system. It just sends all the everything that's happening, sends it out on the wave bus, and then the client front end sits there and manages client state. So that's nice simplification here down in the boiler room of the Waveserver. Because all the traffic is broadcast to everyone, it means that access control is something that's shared. So the Wavebus clients are trusted components that have to engage in the access control. They are responsible for performing access control for their clients. So the data structures inside the Waveserver component is there's a wave map that it maps wave IDs to waves, so to speak, and where the waves are represented by a map from wavelet IDs to wavelet containers. A wavelet container contains the state of a wavelet. So the most important part is the delta history. So I drew this little diagram here to explain that the delta history is a list of contiguous deltas starting from version 0. Each delta has a version, the version where it applies at, and each delta has one or more operations. So these little circles inside are operations, and the triangles are the deltas. So you see how the version numbering follows the number of operations inside the deltas. So not every number is a valid version, only those that fall on a delta boundary. Then another, the rest is, and then see. So this, then we also maintain a snapshot of the wavelet state. So this is something else also described yesterday. So this is so one when you apply all these deltas one by one to the empty wavelet state, then you end up with the current wavelet state, which is the ordered set of participants. It's and the map from document IDs to documents or blips, and a little bit of metadata like the creator, namely the author of the first delta, the creation time, which is the timestamp from the first delta, and the current version. There might be others that we maintain, like last modified time and so on, which is the timestamp of the last delta. But it's all derived from the data within the deltas. And then we maintain the last committed version, which has to do with this commit notices that I'll return to. So when a client of the Wavebus, say the client front end of the robot proxy, submits a delta, such a delta. So this, let's see, I have this diagram here. So a submitted delta is one of the red ones. They're coming in from a client of the Wavebus. In the delta, there's an author. There's one or more operations, and then there's the target version. So in the diagram, it's the downwards route red arrow. It's the version within the history of the wavelet that the version of the wavelet that the client was thinking of when it formulated this delta. Now, the concurrency control in the system with the operational transformation means that the client could have seen one thing and thought of applying a delta there, but the world has moved on. Others came in concurrently and came first and added these deltas. So here in this picture, the leftmost red delta is the one that the client was thinking of. The last two deltas here in the delta history were things that had arrived that the client hadn't seen when it came with this delta. Then by operational transformation, this delta is transformed across these two deltas, and once it's transformed up so that the target version points at the current version of the wavelet, then this transformed delta can be applied. So these deltas at the bottom are transformed deltas that so they look very similar to a submitted delta. They have a list of operations and an author. The version of a delta down here is the one that they were actually applied at, and then they have this extra field of an application timestamp, the server timestamp at which time the transformation was complete and the delta was applied. Once it's so the server does its operational transformation and validity checking, sees that it makes sense that these. So, for instance, if it's let's say it's a add participant, you can only add a participant if the participant wasn't already there, and it has to be syntactically well formed. If it's a document operation, it has to be well formed in the way Alex described yesterday. If it's all good, it's applied, and then it's broadcast on the wave bus so everybody learns that the delta history has grown. So the current implementation has the wave map and the Wavelet container. It's all held in memory, so that's nice and simple, but of course not super useful that all your waves disappear when you restart your server. So we should persist the wave data in the inside the Waveserver, and so there are a couple of patches with implementations of persistence. One from March by Anthony Watkins and Steve Baker, and another one from June by Václav Sikora. So it's a little bit unhappy story about what has happened to these patches. So we messed up the code review of Anthony's earlier in the year, and then so it was hanging around. But in August, when we put more resources on Wave in a Box, we took a look at these patches again, and we communicated with Anthony and Steve, and came up with and decided that we would piecemeal get persistence in. So first, let's see, Leonard took just the certificate store. I'll describe that in a moment, what the certificate store is. It's now has a persistent implementation in using MongoDB. Then Joseph and I and Frederic Gaubry wrote up a design for a file-based wave store. So I'll show you that to you in a moment, and let me do that now. So let's see what happens if I click here. Yes. Actually, there's one thing. Let me. I'll come back to this slide, but let me just say a few words about commit notices. So this is to understand exactly how persistence is intended to work and how it works within the Google Wave production system. And so we decided to broadcast these applied deltas immediately when they're applied and not wait for them to be persisted. And then on the both on the federation protocol and the client server protocol, a commit notice is sent then as a follow-up notice that when later the delta is persisted. The purpose of this was to optimize latency. We wanted, we believed that it was a key product differentiator that the live typing was really live, and that you would see things happen instantly. That also spelling corrections and everything would just would come with a minimum delay. Furthermore, so once you go this route, you quite efficiently hide the latency of the actual write, and you can then start batching writes on the Waveserver to gain some efficiencies in storage access. So there's a trade-off here. The more you delay the write and the more you batch, the bigger you grow the window where you could have a a crash, and you can lose that data that you have told everybody about. And that concept that there's data traveling around the system that might be lost is the drawback to this approach. So it adds complexity to the protocol, the very existence of these commit notices, and then what is the client supposed to be doing with them. So it has actually caused us a number of problems, and we're not entirely sure whether it was given out totality of experience, whether it was a good choice we made. So one of the things that we've had problems with is cache invalidation, that we were sloppy and cached just the most recent data running through the system, rather than be disciplined about only caching things we knew to be committed, and that has given us a number of problems. So the way it can work, if you are disciplined about only caching committed data, the system can be made to work. One of the things that makes it work is that the client buffers the deltas after they've been the deltas that it has sent to the server. It holds on and waits for them to be committed, and keeps the applied deltas, its own applied deltas, around until it gets the commit notice. And if the connection drops and the Waveserver has crashed and lost the data, then it goes into it activates some recovery logic where it tries to when it reestablishes the connection and tries to find out what's the state of the wavelet on the server. And if it then can determine that the server has lost the deltas that it had once applied, then it reapplies them. So we're sort of halfway there with the code that you'll find in the client-server protocol under the concurrency control in the concurrency control package. So we have there's some ways it could be improved and be pretty robust, but it's sort of it is one of the places where it falls down is if there's been actual concurrency, so that the data that's lost are from multiple clients, deltas that have been transformed against each other's, then the current recovery logic comes up short. Anyway, so the commit notice is key to understanding how the wave store should work. So let me go to the wave store design here, which is up on the site pages. So a key requirement if the commit notice tells everybody that now you can rely on this having reached permanent storage, then the wave store should honor that. And so in terms of database terminology, this is a question of durability. Can you say that something has been durably stored? So that made us when we took a closer look at MongoDB, it actually doesn't promise that in a single server configuration. And so we were first thinking of using MongoDB as Anthony had done, but then in order to get a first implementation where we can be clear about the correctness of the solution, we decided to go with a file-based system instead. So the Java file APIs has a concept of durable storage. You can what's called force a file to disk, and then you know that it has reached persistent storage. So let's see. So that if you put things directly in files, then it looks like this. So the design, the file-based design here says that there's a a file per wavelet with the deltas in them. So here, let's say we have in the wave store we have 2 waves, foo.com w plus something here, and another here bar.com something. This so let's say we have 2 wavelets here in the first one, the conversation wavelet and a user data wavelet. Then each wavelet has one file with deltas where the deltas, the transformed deltas, are stored back to back. They are then put in a directory structure here where there's a directory per wave. And then because these, to be absolutely sure that we have some file names that are clean in every file system, we were conservative and took the wave ID and in UTF-8 and took the bytes and hex coded them up into an ASCII string here, and similarly with the wavelet IDs for the delta files. Then there are 2. Okay, so this way you can look it up, right? The wave store does a directory lookup to find the wavelets in a wave by looking at the file names. There are 2 files per wavelet. One is, oh man, that looks terrible, wrapped around. Yeah. I don't know if that's possible to see. Otherwise, go to the design doc. So the deltas file has a file header with some version information, and then each record again has some version information so we know the format. And then there's a header and a body. The header just says what the sizes of the components in the body is, and in the body we have 2 things: the applied delta, which is an adorned delta with some federation information that I'll come to now, and then there's the transformed delta that I talked about before. And then for efficiency, there's also an index file. I'm not going to describe that in detail, so that's sort of an that allows for efficient indexing of the positions within the file where the deltas are. So let me go back here. So where we are with this is that Joseph has implemented the delta store that writes out these files. It's not yet hooked up to the Waveserver, the Waveserver and Wavelet container classes in the Waveserver, so it's not operational yet, but we're getting there. So there's some question marks here about inbox and search. We haven't arrived at a design for these things yet, so it's probably better I just shut up about it. There's some thoughts about it in the design doc, and we have some ideas, but we're very open to inputs here. All right, let me quickly run through federation. Let me just see. I could also save the rest for the federation talk in the afternoon. Because we're already running over. I'm already running over time. I just want to say. Let me just talk about it very briefly. So here again is the diagram with the Waveserver and the Wavebus. On the Waveserver also talks to an XMPP server, a federated instance of Wave in a Box also talks to an XMPP server and federates with other Wave servers out there in the cloud. What it does on the XMPP side is depends on whether Wavelet is hosted by this Wave server or whether it's hosted somewhere else. So for local wavelets, a wavelet whose wavelet ID, so with the red here is the So each line here is a wavelet name consisting of wavelet ID, wave ID followed by a wavelet ID. So the domain name in the wavelet ID says where it's hosted. And let's say that this is the Waveserver for foo.com. Then these first 4 wavelets hosted at that it hosts are local. And for a local wavelet, it does exactly what we just described. And then for federation, it basically publishes this wave bus to or XMPP to other federated servers. So it looks up all the participants, the domains that are on participants in the wavelet, and then it sends the traffic on the wavelet out to those domains that it finds over XMPP. And then it accepts that they the wave servers from those domains, they can come and submit deltas from those participants, the remote participants, and they can come and make history requests to learn about the past history of the wavelet. For a remote wavelet, so here's the one here at the bottom, so that's hosted by bar.com. Well, for such a wavelet, the Waveserver for the foo.com Waveserver works basically as a caching proxy. It serves up this wavelet for its local Wavebus clients, and it keeps a local copy of all the wavelet state that it knows that it serves up to them. It then receives from the hosting from bar.com, the hosting Waveserver, or XMPP, it receives the deltas that is that bar.com broadcasts to it, and it then forwards them to its local Wavebus. And then when local clients submit deltas, then foo.com's Waveserver doesn't do the operational transform and so on. It just forwards it to OXMPP to the host server, and that way it sort of works as a proxy between for the local clients towards the actual host of the wavelet. I'll save all this signatures and search stuff for the federation talk, yeah. So I already mentioned persistence and indexing as 2 things that are work in progress. So the history of the Wave in a Box Waveserver, which was once called Fed1, so it was done quickly for a particular event in July last year, and so it's good that it's simple. There's not a lot of cruft that has built up, but it's also too simple in places. The error handling is too simplistic, and we need some more unit tests to make it easier to work with the code base. Yeah. Then that apart from persistence indexing, there are a couple of other things that we should be doing. For indexing, we should enhance the Wavebus interface so that you can reliably deliver messages, deltas across the Wavebus. It doesn't work to index if you only index away when you're lucky and things don't crash. So we have some ideas for how to do that. That borrows from what we did in the production system. But I can share those. If you want to know about that, I'm happy to tell more about that. Then we are too lax about enforcing certain constraints on wavelets, so that we should be policing a couple of things. We had a system of policer classes that were running inside the Waveserver that are doing that in the production system, and we should probably do the same for the Wave in a Box server. And then there's certain efficiency and scalability things that are not there that will be useful to work on once we have a feature complete. Yes. I think I'll skip the code walkthrough. So Joseph did explain where some of this code is located. Basically, all of this is inside the Waveserver package, plus one or two classes over in the persistence package. I'm happy to, over the coming days, I'm around, and if you want to know more, please come and ask. Questions? Yes?
What's the pros and cons and possibilities of actually moving the server into a more sophisticated container, like a WebLogic server or a WebSphere, where you actually get some of things like policy management, security, and user management, that sort of other things, sort of for free as part of the container. Why did you choose sort of not to do that? Is there any reason to either stay away from doing that in the future or to look at potentially doing that?
One thing is I'm rather ignorant about these things, so it's possible that I should repeat your question. So your question is
why not host it in a J2E container? You could make the server essentially a JCA or something, like adapter, a transactional adapter, and then right. All the things that sit on the front of the Wave bus could essentially be clients to a JCA framework, for example.
Yeah. So the question is, why not build the Waveserver in a JCA container that has many of the features that we need here, or something of that nature? And that's in part by the historical roots where we wanted to do a bare bones simple system where you could see end to end where the bits was traveling through the system, and in part out of ignorance because we're not very well versed in these things. I can't give you very informed analysis of the pros and cons. Okay, so I ran over time, so let's move on to Christian.